Hello students, welcome to lecture 30 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on application of metasurfaces and GMR devices. So here is the lecture outline. First we will see some of the metasurface based devices such as metasurface based lens and sensor. We will go into the details of how these things are designed. And then we will look into some of the applications of GMR based devices, that is guided mode resonance based devices. We will discuss about some band pass filters as well as GMR based sensors. So metasurface, I hope you all remember from the previous lectures that metasurface gives you the control on the amplitude, phase, polarization, also on the frequency of the incident light. You can modify those using metasurface. So the modification can be seen either on the reflected wave or the transmitted wave. You can also see some other applications, something like OAM, that is orbital angular momentum. Okay, we can have diffraction order, space dispersion and all these things. They also have application in wavefront engineering. These are called basically wavefront engineering, holography, advanced manufacturing and intelligent surfaces. So we will come into each of these briefly. So first let us focus on wavefront in engineering, and we understood that metasurface can serve as promising platforms for high performance optical elements such as metallands, then structural light generators, polarizers, wave plates, optical isolators and so on. So these are the applications of wavefront engineering. You can also use metasurface for holography because they can act as excellent holographic recording medium, and this is because of their large information capacity and sub-wavelength wavelengths units basically. You can take help of intelligent algorithm, and in that case metasurface can significantly simplify the design, assembly and operation of optical systems. You can also take help of inverse design algorithms to design metasurfaces for a particular application. So here in inverse design means you know the desired response and you ask the software to optimize the parameter space and give you the design which will be closely matching to the desired optical response. With the support of advanced fabrication, metasurfaces with larger diameters and more complex structures can be made, and that will allow you to achieve better performance and also complex functionalities. And the other important thing is that with the excellent properties of metasurfaces, you can also develop advanced fabrication technologies such as nanoimprint lithography and resonant laser printing. So metasurface can also help improving the standard fabrication technologies. So these are also some applications that we can foresee. You can think of intelligent optical chip based on metasurfaces, multifunctional camera, light field imaging, you have holographic multiplexing, optical calculators and so on. So all these things are possible using metasurfaces. Now let us take one particular example of a lens design based on metasurface. So here we are going to design a metasurface based broadband flat lens array. So this is the unit cell design to start with. So it is basically a C-shaped split ring resonator, as you can see, and this dashed line is basically the symmetry axis, and you can see the symmetry axis makes 45-degree angle with X axis. Okay, and why do we choose this? I will come to that. The schematic of this C-shaped SRR, where the parameters are basically this. So the radius, the outer radius of the ring is 35 micron. Alpha is this opening. You can see there is a cut. So this cut opening makes an angle of 10.5 degree. Okay, here it is definitely more, but this is just a schematic. Okay, So, and then you have W, that is the width of this ring, to be 5 micron. Now, how it works? So, we position the symmetry axis as plus minus 45 degree with respect to x axis, and then this SRR are basically made of 200 nanometer thick aluminum, okay, which has got a conductivity of 3.72 10 to the power 7 Siemens per meter, and you can pattern this on top of a silicon substrate which has got a permittivity of 11.7. Okay, so you can consider epsilon silicon as 11.7. Now, what is the good thing about this? You can see here, okay, so you have taken different shapes of this unit cell, and you can actually calculate the amplitude transmittance through a infinite array of this kind of unit cells when repeated periodically in both dimensions, and also you calculate the phase shift that is plotted here in this particular right axis. Okay, and these are all done for the case where your incident light is expolarized and you have chosen the frequency to be 0.8 terahertz. Okay, and these are the 8 different unit cell designs of the split ring resonator, as you can see, and the output light is basically y polarized. So, here you can see this is x and y. So, this is the detected light, that is y polarized, and the incident light is x polarized. Okay. So, here you see that the first 4, if you look into the first 4 designs, they have slightly different split ring. Okay. So, somewhere the opening angle is changing, somewhere the position is changing, and so on. Okay. So, here it is basically the opening is getting bigger and bigger. Okay. So, that actually helped us to do one thing. So, you have actually calculated the transmittance in these 4 cases, and you can see they are more or less equal transmission amplitude. However, the phase, if you see, the first one has got a phase of 0 degree, then 45 degree, then 90 degree, and another 48 degrees, so it's 135 degree, and so on. So, these are allowing you to add a phase difference of pi by 4, pi by 4, pi by 4, and so on. So, this opening is allow you to add the phase. Okay. Now, the phase shift of the outgoing y polarized light can also change by pi when the resonator is mirrored by 48 degree. Okay. Oh, sorry, the resonator is mirrored along the x axis, okay, while keeping the transmission amplitude invariant. So, that is how you actually got this additional 4 resonators. So, if you take a mirror of this particular design with respect to x axis, you come up with this one. So, this will give a pi phase shift as corresponding to this one. So, this was 0. So, this guy has got a phase shift of pi. Okay. Similarly, this design had a phase shift of it is actually 135 degrees. So, you can actually see what it will be. So, 135 plus pi. So, that will be the phase here. So, you can actually go up to, so you can start from here. So, you can say this is pi, and then you can go up to 2 pi. Okay. So, that way you are able to get starting from 0 to 2 pi all the phase you can actually see you are able to achieve for all these different designs of the unit cell, and you are keeping the amplitude more or less constant, amplitude of the transmission. So, this is the beauty of this particular design. Now, if you do the similar kind of thing, okay, for say the opposite orientation, that means if you consider incident light to be y polarized, you will get similar results for transmitted or transmitted wave, which will be in that case x polarized. Okay. So, same thing can be repeated once you exchange the polarization. So, it will work perfectly fine. In that case, you have to also take the mirror across the y axis. Okay. So, this is how the different designs of the unit cell allows you to achieve more or less similar transmission, but you are able to manipulate phase at particular interval. Now with that you can design a flat metasurface lens. So this one, the slab that you see here is basically that particular metasurface lens, which is a flat lens. And when you are designing this flat lens using those split ring resonators we have just seen, you are able to achieve a hyperboloidal phase profile like this, okay, and this will allow you to engineer the transmitted wavefront, okay, in such a way as if it is coming from a conventional lens, and that is how a flat metasurface will also be able to focus light from here to this particular point. So this is what metasurface will be able to achieve. Now here we have assumed that the plane wave travels along z direction and it will come to the metasurface like this. From the metasurface it will get focused at a particular focal point f, and small f is the distance, focal length. And here you see the blue sphere surface is basically the equiphase surface, okay. Now according to Farnet's principle, the hyperboloidal phase profile can be expressed using this formula, where phi r and phi 0 basically represent the abrupt phase shift at an arbitrary point r. So this is any arbitrary point r and the origin is basically O. So this is at that r point and this is at O point. What is lambda? Lambda is basically the wavelength of the light in vacuum, okay. Small r is basically the distance from of this point which is having coordinate x y from the origin. So it is square root of x square plus y square, and f is the focal length that you are designing. So based on that you can actually see you can alter the focal length. You have to choose that particular element in that particular way, okay. So here the placement of those different elements that you have seen, that will decide what should be the focal length. So you have got complete control on designing this kind of meta lens. Now let's take one example. So let's fix that the focal length should be around 10 mm, okay, and you are using those 8 resonators in a particular pattern to realize this particular meta lens, okay. So here you see the diameter of the lens is designed to be of, so here each of them are basically one of those meta lens. So the diameter is taken to be 5.52 mm and it has got a numerical aperture of 0.27, okay. And here you see this is basically the profile, okay. So this one is how the phase shift changes, okay. So as you go inside, the darker colors they look like having higher, so this red colors they look like higher phase 2 pi, okay, and here the blue one is having very low phase shift. So that way it is not patterned in a particular fashion, it should have a hyperboloidal kind of pattern so that you are able to focus that light beam. So you have to introduce the phase to the incoming light so that it can band and focus at a particular point. So this shows the design of a single lens in the metasurface, okay. It also shows the distribution of the phase and the 8 different resonators, and the space for every unit is basically 80 micron by 80 micron, and here the time scale the length scale is 1 mm. Now this, if you take this particular portion and zoom it, you will see this is how you have placed your meta lens. So you see meta lens design will require help of numerical simulation tools to optimize the design so that you can have a focal length of 10 mm or whatever is your requirement. So it depends on the placement of these elements, you will be able to change the phase shift profile. And this is the schematic of 5x5 metasurface lens array which is patterned on a silicon substrate. So what is the advantage? As you can see here, if you think of traditional terahertz lenses, they are basically bulky, and they are bulky because they rely on the phase accumulation of the wave while it is traveling through the lens, and that gives you the focusing of the wave. here it is different. Here in metasurface, your surface is introducing the phase. So, metasurface lens can be flat, thin and flexible. So, this is why metasurface lens has got a lot of application in the future. When you do the analysis of this, let us first look into the simulation results. So, these are the simulation results of the metasurface lens. Okay, it is used as a cylindrical lens. So, these are the simulated electric field distribution for X polarized light incident normally. Okay. So, here only the normal components are basically only the wave components with polarization orthogonal to the incident beam is shown, and the structure was designed for 0.8 terahertz. So, you can see the focusing over here, but you can also see that it is working fine for other wavelengths, something like 0.5 terahertz as well as 0.6 terahertz or 0.9 terahertz. So, it actually has a very broadband functioning range. Okay. And the focal length, you can actually see that the focal length is decreasing with frequency. Okay, so 0.5 has got a smaller or shorter focal length as compared to 0.8, whereas 0.9 will have a larger one as compared to 0.8 terahertz, and this is pretty good, because here also from the equation you can see that is happening. If you look at the experimental results, so these are the experimental results. So, here also you can see the focusing is taking place. So, here again we are considering X polarization, normal incident light. So, A to H are basically showing you the Y polarized electric field amplitude distribution in ZX. So, this entire column is for ZX cross section, and this entire column is for ZY cross section, and this particular column shows you from the focal plane. Okay. So, whatever is, so if you actually take a cut at this particular point, you see this nice focusing happening. Okay. So, this actually gives you evidence that the lens you have designed using this kind of C-shaped split ring resonators work pretty well, and that not only works for the frequency that you have centered it around, you can also work on the frequencies adjacent to that. Okay. So, let us now look into another design based on metasurfaces. Let us look into a sensor made of metasurface. Now, photonic biosensors have recently got a lot of interest, okay, and detection using biosensors may come handy due to their multi-purpose applications, something like sensing, encryption, etc. Okay. So, you can think of making a sensor, okay, or you can say metasurface refractive index sensor, okay, that is constructed by placing a graphene pattern sheet. So, here you can see this particular structure is made up of graphene. So, you have taken a graphene sheet and patterned it, and then you put it on top of a glass material. Okay. So, this is how the structure is. So, if you see, this is the three-dimensional perspective, this is the top view and this is the side view. So, here you can clearly see you have graphene, you have peptides, okay, which is the surrounding medium, okay, and then you for detection, that is how it will work as a biosensor. Whenever there is a change in the refractive index, the resonant wavelength will show some shift, and you can detect that shift, and that will be the detection. So, this is the structure. So, here the glass substrate is 10 micron by 10 micron by 1.5 micron, this is the thickness, and when you pattern the graphene in the metasurface, so this is the metasurface which has got a unit cell dimensions of this one. So, this length is 9 micron, LT, which is the end of the length of the tail end, that is 4 micron, and you have width of the tail end, that is 0.5 micron, and the overall thing has got a single layer graphene thickness, that is 0.34 nanometer. Now, first thing is to know what will be the permittivity of this graphene material. So, you can actually estimate that from the graphene's conductivity. So, for a single layer graphene sheet, the graphene conductivity can be split into two parts. That also you can do for multi-layer, it is not only necessary for single layer. So, it has got two parts like intraband and interband conductivity. So, you can write the permittivity in terms of conductivity then. So, epsilon omega can be written as 1 plus sigma over epsilon naught omega delta. Okay. From that, this sigma s has got two parts. This is intraband contribution and this is interband contribution, as you can see here, and you can observe that omega is the angular frequency that you are using, and this delta, as I told you, this is the thickness of the sheet, okay, graphene sheet. So, for single layer it is 0.34 nanometer. You can also put multi-layer over here, whatever is the thickness, that will change the permittivity. Okay. And in this formula, T is the room temperature, Kb is the Boltzmann's constant, and H cross is basically the reduced Planck's constant. So, using this formula you can find out what is your sigma s. From sigma s you can estimate what is the permittivity. Okay. You can also correlate the chemical potential of the graphene, okay, with the capacitance, voltage and the Fermi velocity. Okay. So, this is also a way to find out what is mu c, that is the graphene's chemical potential, and they will be applied into this particular equation of conductivity. So, with all the parameters known here, okay, you can obtain the permittivity, and that allows you to also find out what is the impedance and refractive index based permittivity and permeability. So, you can see that the impedance can be calculated from the S11. So, if you take this kind of unit cell and then periodically extend it in both x and y direction, and you put two ports, one along Z plus and one along Z minus. Okay. So, you can obtain what is the S11 parameter, there is the reflection parameter. So, reflection, so port 1, say light is coming from port 1, which is on the top of your sheet. Okay. So, S11 will be the reflectance or reflection coefficient, and S21 will be the transmission coefficient. Okay. So, from that you can also obtain this parameter e to the power I n k naught d can be related to this S parameter and the impedance. That allows you to calculate what is the refractive index. Okay. So, refractive index can be correlated with the permittivity using this formula, which is epsilon equals n over z, and permeability can be written as mu equals n z. Okay. So, this is how you can obtain the parameters for this particular graphene based structure, and then you look into the performance parameter for this particular sensor. So, you can understand that there will be a transmission dip for this particular sensor, and when you change the surrounding media refractive index, the transmission dip will change. Okay. So, in that case you can find out what is the sensitivity of your device when it is working as a sensor. How it is sensing? You are changing the surrounding medium permittivity, accordingly the transmission dip wavelength is basically changing, right. So, you can find out sensitivity equals delta f, that is the change in the frequency over the change in the refractive index of the surrounding medium. You can also find out the figure of merit of this sensor as S divided by the FWHM of this, that is full width half maxima of one of this dip. Okay, fine. So, this is how you can use metasurface based devices for lens, for sensing and all these things, and they are pretty sensitive devices that you can make using metasurfaces. So, now let us look into some example for GMR based devices. So, GMR, if you remember, these are basically guided mode resonance based devices, and as I mentioned in the previous lectures that GMR gives you excellent filters, very high quality filters. So, let us look into a design of flat top bandpass filter for terahertz telecommunication application. So, here is a structure that is freestanding, and it consists of gold film which is periodically pierced. As you can see, these are cuts in the gold film. As you can see, this is the actual image, and this is the schematic, and it is basically sitting on a thin film of silicon nitride. Okay, so we are calling it as SiNX, and the permittivity is 1.97. Okay, and this is a gold film, and here are the parameters for this one. So you have the periodicity of this grating that you have created. This is basically a 1D grating. Okay, it is this is the grating period. Okay, W is basically the width of the slit, 215 nanometer. Tm and Td are basically the height or the thickness of the metal layer, thickness of the dielectric layer. That those are 70 nanometer and 540 nanometer respectively. Now there is a way to choose this period of the grating. It should be chosen such that the resonant wavelength lambda aha, okay, the first diffracted orders are trapped in this silicon nitride film. So when you first diffracted order means you are talking about +1 and -1. So you are letting the 0th order to escape. Okay, so you have to make sure that there is total internal reflection. Okay, and total internal reflection, you can think of the condition here. This is the range of lambda r. Okay, when it is normally incident. So you will get total internal reflection from this bottom interface, and you should get high reflectance from the top interface, which is basically the narrow slits in the gold film. Okay, so this is what should happen. So you are having incident light falling from this side on the grating, okay, which has got sub-wavelength metallic grating deposited on freestanding dielectric layer. Here in this case it is silicon nitride. Okay, and you want the first order diffracted waves to be trapped inside and the 0th order to come out. Okay, so this is how you will be having bandpass filter. So they too will block, okay, and this will only pass. So let us see how we do this. So to do this, we need to understand the diffractions from the grating. So we should understand the grating equations. So here you see a schematic shows only a grating, and then this is the incident wave vector, and this is the transmitted wave vector, that is the 0th, the fundamental one, and the 0th one shows the reflected fundamental wave vector. Okay, and there are +1, -1, +2, -2, okay, +3, these are not shown. Okay, so only +-1 is shown for the reflectance, and for transmittance +-1 is shown, +-2 is also shown, and beyond that it is not shown. Okay, so what are the equations for the reflection region? This is the equation. So Nref is the refractive index of the this particular medium. Sin theta m, okay, will be equal to n incident sin theta incident minus m lambda naught over capital lambda x. So capital lambda x is basically your grating period, m is the order. Okay, so here you can find out all those different angles in which the reflection will take place. Similarly, you can also find out for different m equals 0, +1, -1, what will be the condition that is satisfied, and you can obtain what are those angles through which the transmission of 0th order or +-1, +-2 order will take place. Now these grating equations, they allow us to relate the wavelength of the incident wave and grating to the angle of the diffracted modes. So that is very good. So this is how the angles are related to these wavelengths, and you can also predict the directions and the power of the diffracted modes. Right, the directions means the angles will only tell you the direction. So this information you can obtain from this grating equations. Now coming back to this structure, we considered the metal layer to be 70 nanometer and the slits are very narrow, which are 215 nanometer, and this ensures a polarization sensitivity. What does it mean? It is designed in a way that the TM polarized waves are basically transmitted through the slits, okay, in which case the electric fields are like this, but the T, that is proportional or parallel, where the electric field is parallel to X, will be basically reflected from this metallic membrane. They will not be able to pass through, okay. And this particular thickness of the dielectric layer and the grating period, that is D, okay, is selected such that you only get single transmission peak, okay. And here the design is meant for 2.97 micrometer and you have chosen normal incidence. So, this is basically the incident angle. So, here you have considered theta to be 0, okay. So, such filters, this kind of filters can be very useful for atmospheric observation, which has got a transparency range from 2.8 to 5 micron. So, here you can only allow single transmission peak. So, you can use it for this kind of atmospheric observations. And how the design will change, this particular method of redesigning a filter easily is also called frequency scaling. So, how it works? So, say instead of 2.97 center wavelength, if you want to double the wavelength, okay, that means you want to scale your design, okay. In that case, all the physical parameters of the design will also get doubled, okay. Something like the periodicity, the width and the thickness and all these things will also get doubled, okay. So, you can scale it up, so that will allow you to get that, okay. Now, let us first focus on this particular design, which was meant for 2.97. So, it is, you can see here it is speaking at 2.97. So, this is the transmission spectrum of the TM polarized wave for this particular design, okay. And the inset shows the magnetic field intensity, which is modulus of Hy square, okay, for this particular incident on. And gold has been assumed to have a refractive index, which is given by this particular equation, okay. So, you can actually obtain the gold permittivity using these equations. Here two important things are seen. So, this is basically the gold membrane and this layer is basically your silicon nitride, okay. And figure B shows the transmission maximum in the left axis and its spectral position. So, where it happens. So, everything is changing when you change D, okay. So, you can change the periodicity and you can tune the resonance position as well as the transmission maximum. So, here you are just keeping gold and the silver layer, silicon nitride layer thickness constant, okay. So, that brings me to a case where the scaling actually takes place over this lattice period, okay, and the width of the slit, okay. So, these factors, the thickness factors will not play a role, okay. Now, if you look into the optical transmittance diagram, which is T as a function of sigma and kx, okay, this is how it looks like. It is a parametric plot. Here sigma is basically 1 over lambda, that is the wave number, and kx is the x component of the incident wave vector, and kx can be calculated as 2 pi sin theta over lambda. Now, here a couple of important things are there. So, this diagram, as you can see, is divided into areas corresponding to the existence of propagative diffractive orders in air. So, here you can see only 0th order is coming out, but plus minus 1 modes are excited. Here 0th order is coming out, but only plus 1 is excited. Here 0th order is coming out and no diffracted modes are excited. Here it is 2 modes are coming out. So, 0 and minus 1 is coming out, and plus 1 and minus 1 are also getting excited. So, okay. So, from that two modes are getting coming out, only plus one is getting trapped. Okay. So basically there are different regions and which are separated by this different white lines, as you can see. So if you see the plus minus 1 diffracted orders in free space and silicon nitride, so this is in air, okay, and this one is in the silicon nitride, okay, and zeroth order transmission spectra have been measured for the incident angle ranging from 0 to 45 degree. So this is the case where you have theta equals 45 degree, okay, and that has been done with 0.5 degree increment for TM polarization, and those transmission plots are actually here. So the bright color shows highest transmission and darkest color shows almost zero transmission, okay, and there are two transmission bands corresponding for two modes. So you can see there are two transmission bands here for the two modes of silicon nitride layer. What are the two modes? One is basically the plus one and the minus one, okay. Now as expected, high transmission is measured when no diffracted waves are transmitted in air. So that is below this particular dotted line. Above this dotted line there is a diffracted mode is also transmitted, so you know the transmission drops. So but here no diffracted modes are there, so you get very strong transmission, okay. However, in the silicon nitride layer, that is here, okay, diffracted orders are required. So the zeroth order cannot couple directly to the guided mode of silicon nitride, that you can understand. So zeroth order cannot directly get coupled to silicon nitride, and that is why also they are simply coming out, because in order to do that you need to have wave vector matching, or you can say that there is wave vector mismatch between the zeroth order, and that is why zeroth order will not get coupled directly as guided mode. However, for plus minus 1 diffracted mode in the silicon nitride SiNX layer, okay, it can give you those two guided mode resonances, which we are able to see that when there are two guided mode resonances, the transmittance become bright, okay. So these guided mode resonances are basically in the silicon nitride waveguide, and they actually are transmitted by a second coupling with the gold grid. So when you measure them, okay, so you can measure the absolute transmission intensity, and you can see it reaches 78% at normal incidence, and that is basically almost 8-fold enhancement compared to the geometrical transmission, and that is significant. So without the guided mode resonance effect, you will hardly see any significant transmission here, okay, you will only see like 10% or something like that. So you can calculate the FWHM, that is 2 to 3 nanometer, and when you do it for 10 degree, you are seeing two different transmission peaks. So you are also getting a second peak at 3.3 micrometer, which corresponds to the excitation of second guided mode resonance, okay. So that is happening. So when you go towards this, so this is the axis where theta is 0, this is where theta goes to 40 degree. So you are actually able to see more modes coming in, and there is also another little peak visible at 4.3 micrometer, and but this is corresponding to carbon dioxide absorption during the fabrication. So this is a fabrication issue. Other than that, these are the two things that completely matches our prediction. So next thing is, as I mentioned, GMR based devices have very high Q. They can also be used for sensing application. So let us look into GMR based biosensors, and it is very popular to use GMR effect for sensing, especially in biosensing, because they have very narrow controllable line width and they make very high efficient filters. And there are four main detection schemes for GMR based sensors: wavelength detection, angular shift detection, intensity shift detection and phase shift detection. Among this, the top two, that is wavelength detection and angular shift detection, they are the most commonly used one, as incident light is totally reflected with highly angular and spectral selectivity at resonance. So, you can see the schematic here. The schematic shows, so this is where you have the grating, this is your waveguide and this is the substrate. So, this is the GMR resonance device. So, incident light passes through the grating with an incident angle. So, here the incident angle is theta I, okay, and the grating equation will be the gamma, capital gamma, that is the grating period, NWG, that is the refractive index of the waveguide, sin theta d, that is the diffracted angle, okay, minus NC, NC is the cladding refractive index, sin theta I, that will be equal to mg, that is the order of the diffracted wave times lambda. So, what is mg? It can be 0, plus minus 1, plus minus 2 and so on. So, this particular diagram can also be written, okay, we will discuss this later. So, it is like, you know, this can be seen also like this, where, you know, the, so this is basically a simplified model of your GMR sensor, where the height or the depth of the grating is assumed to be 0. So, here you just show top layer, waveguide and substrate layer, and you are just showing what is happening, okay. So, this is the diffracted wave, and then it gets, you know, totally internally reflected and so on. This is how it propagates inside this waveguide. Now, the grating diffracted wave will couple into the waveguide layer once the diffracted wave is phase matched, that we all know, that only. So, there is diffraction, but when it is phase matched, it will be supported in this waveguide and it can propagate. So, theta d is the propagation angle in the waveguide layer, and we, for simplicity, we can think that this dg, the height of the grating or the groove, okay, should be, can be extremely thin or small, and they can be ignored. So, this allows us to look for the conditions of phase matching. So, the guided wave condition of the planar waveguide can be defined from this one. So, if this is theta d, this angle is theta d, okay, and this wave vector is k naught, okay. K naught is basically the incident, k naught is the wave vector in air or in vacuum. You multiply this by the refractive index of Ng layer, so you get the wave vector in this one, okay, and then you can take the cos theta component, okay. So, you will get this one basically. So, this one minus m phi, okay. So, this cos theta d, okay, will give you the vertical this particular one, okay, the component of the wave vector, and when you take minus m phi, that should be equal to the total phase that is there and the top and the bottom of the two interfaces, okay. So, you can write k naught is basically 2 pi by lambda, which is the wave number in vacuum. dwg is basically the thickness of the waveguide, or that is the height here, okay. M is a positive integer, it is basically the mode number of the waveguide. It can be 0, it can be plus 1, minus 1, plus 2, minus 2. And phi top and phi bottom, as you can see, these are basically the phase shifts that occur due to total internal Fresnel reflection at the top and the bottom interfaces. So, top interface is basically the waveguide grating interface, and the bottom one is basically waveguide substrate interface, right. So, for a given waveguide structure, you can use this particular equation to calculate what will be theta d, okay, and then you can use this equation to find out what is the theta I that will give you that theta d, okay. So, that way you know the incident angle that will allow you to get this particular modes. And then when the surrounding refractive index NC change, what will happen? Different incident angles can be resolved, okay. So, you can actually obtain the angular sensitivity like this. So, you can define angular sensitivity as SA, which is delta theta I, that will be the change in the incident angle whenever there is a change in the surrounding refractive index, surrounding medium refractive index. So, here you can say that delta theta I is basically the shift in the resonant angle that is introduced by the change in the refractive index of the surrounding media, that is delta NC. So, here you see this, the first one, it shows the schematic of the grating waveguide guided mode resonance. So, you see there is guided mode resonance for this structure, and that helps for angular resonance, and this also shows the reflection spectrum, okay, in this case, okay, for the refractive index values of 1.333, okay, that is the red one, then NC equals 1.353 and NC equals 1.373, okay. So, you can see they are color coded, and what is important here to notice is that with this kind of change, minor change in the refractive index, the incident angle needs to change, okay. So, that is how it is angular resolved, or you can actually use this as a sensor, right. So, with that we stop here today, and this ends our discussion on metasurface and GMR based devices. In the next lecture, we will discuss about another interesting topic, that will be on transformation optics, and we will see how to make invisibility clocks. Thank you. If you have got any query, you can drop an email to this email address mentioning MOOC on the subject line.